The proliferation of voice-activated digital assistants, or VADA, software such as Amazon Alexa, Google Voice Search, Microsoft Cortana, and Dragon Assistant for computers and mobile devices has created a unique set of testing challenges for researchers, software developers, and users. Speech recognition is the most convenient method for users to input data into mobile devices and smart speaker solutions. Voice input is creating a need to effectively evaluate the speech processing component of VADA systems. Researchers have attempted to measure the accuracy of speech-to-text software programs with several different methods. The methods that have been researched have looked at individual elements of speech processing accuracy, such as word error rate, ambient noise rejection, signal-to-noise variation, and phrase-based language accuracy. This presentation proposes a software testing method that will measure the speech processing accuracy of VADA systems that takes into account all researched methods and incorporates new testing measurements and metrics and returns a score that can be used to correctly compare the speech processing accuracy between VADA software developers' speech processing systems. The new speech accuracy benchmark score and testing technique will create test cases that eliminate the hardware and human variance on speech processing software testing by creating a specific set of test phrases and by defining the hardware setup for the test cases. A typical VADA device system has several subsystems, which may include the manufacturer-developed hardware device, a cloud-based service that holds the user account information and performs the speech-to-text processing, consumer-purchased hardware such as manufacturer-developed hardware, smartphones, tablets, and computers, and connections to third-party clouds, devices, and apps. Speech recognition, or speech-to-text, is the process software programs use to convert spoken audio into text that is readable by computers. Speech recognition, or voice recognition software, made its commercial debut in 1990 in a DOS-based system known as Dragon Dictate. This was a speaker-dependent, discrete speech recognition software engine used to convert spoken audio into text. Discrete speech means one word at a time is spoken, and the output is one word at a time. The second generation of speech recognition was continuous speech recognition. This allowed users to speak in phrases of 4 to 7 words without the need to break between individual words. It also introduced built-in commands which allowed the computer to carry out an instruction instead of just outputting text. In 2011, both Apple and Google released the first versions of virtual digital assistants for mobile devices with Apple's Siri and Google's Voice Search. These software offerings were designed to use a cloud service to process the speech, be speaker independent, use voice authentication, and return output results to the device. Virtual digital assistants were not only able to process speech, but also carry out commands on the mobile devices and computers that they were run on. Current testing of speech processing has been focused on word error rate. Researchers and software developers have relied on this testing method to define the accuracy of speech processing software. McCowan et al. Defined the word error rate measurement for both discrete speech and continuous speech recognition systems. However, this software testing method fails to take into account the accuracy of voice authentication and voice command recognition. The VADA speech processing systems have an AI component processing element. Combe et al. Determined the software accuracy measurement of AI systems must compare the intent of the command with the output. The command error rate testing method proposed in this paper and presentation measures the user's voice command intent against the expected output to determine the AI accuracy of the speech processing system. VADA speech processing accuracy is also affected by the sound pressure level and ambient or background sound present when voice input is instantiated. Zhang et al. Ran software tests with VADA systems and measured the effects on accuracy of sound pressure and signal-to-noise ratio. Previous research into the accuracy of speech recognition systems have not included these testing methods and measurements. This paper proposes including the measurements into the accuracy score for speech processing systems. The proposed speech processing accuracy benchmark score will incorporate 6 software testing elements: word error rate, command error rate, authentication accuracy, rejection rate, signal-to-noise ratio variance, sound pressure level variance, and will return a score between 0 and 6, 0 indicating there is no accuracy, and 6 indicating perfect accuracy by the software, speech processing software that has been tested. Word error rate testing is a commonly used test and metric to describe the accuracy of speech processing software. It has been used by software manufacturers to describe the accuracy of their product and is frequently given in a % format. For example, a speech processing product may be described as 96% accurate. It is a measure of input words compared to output text for correctness. A WIR rating of 0% indicates no accuracy. A WIR rating of 100% indicates perfect accuracy. Word error rate is determined by taking the number of correct words and dividing by the total number of test words. In the case of continuous speech recognition, the number of correct words must take into account the number of substituted words, inserted words, and deleted words to determine the number of correct words. Authentication in a VADA system occurs when the user issues the activation word or phrase. Google uses the authentication phrases "OK Google" or "Hey Google," while Amazon system uses the authentication phrase "Alexa." Authentication is required by VADA systems before any other interaction can take place with the digital assistant software. Authentication accuracy is a measure of the number of times the authentication phrase was spoken compared to the number of times authentication was granted. An authentication accuracy score of 0 indicates no accuracy. An authentication accuracy score of 1 indicates perfect accuracy. The formula for authentication is the total number of successful authentication attempts divided by the total number of authentication attempts. Command error rate measures the output accuracy from the speech processing software when a command or action is issued by the user by voice. For example, open my calendar is a command. Send a text message to John Smith is a command that includes an attribute or additional element to the command. Command error rate measures the accuracy of the speech processing software to carry out a command. A command will be carried out successfully when the user's command intent is fully carried out. The formula for calculating command error rate for basic commands or commands with no attributes is as follows. The number of correctly carried out commands is divided by the total number of commands issued. When the commands issued have attributes, the formula for calculating the command error rate is as follows. The number of correctly carried out commands is added to the total number of attributes correctly interpreted by the software. This is divided by the total number of commands issued plus the total number of attributes issued. Speech processing software has built-in algorithms to ignore different types of sharp or unwanted input sounds. These algorithms are sometimes referred to as and ah filters. They are designed to ignore frequently used space-filling sounds that speakers utter while thinking or searching for the words they wish to say next, such as and ah. These algorithms are also designed to ignore sharp noises such as dog barking, doorbells ringing, or pounding sounds. Developers refer to this process of ignoring these sounds as rejection. A sharp or unwanted sound that should be rejected by the speech processing software is any sound that can be picked up by the microphone that is at the same or higher sound pressure level than that of the speaker and should not be converted into text or command output. The rejected sound should not be part of the text or command output. The rejection rate is calculated by taking the number of rejected unwanted sounds and dividing by the total number of unwanted sounds that should be rejected. In Zhang et al.'s paper, he identified and measured the effect of varying sound pressure levels had on the accuracy of VADA speech processing systems. The research revealed that varying the sound pressure levels and varying signal-to-noise ratios directly affected the accuracy of the speech processing software. In practical terms, the accuracy of the speech processing software should be measured using multiple distances between the device's microphone and the audio output device or user's mouth. When the distance increases, the sound pressure level of the speaker should not change when testing. Sound pressure level measurement is expressed in decibels and indicates the atmospheric pressure caused by a sound wave. Sound pressure is measured using a sound level meter. The sound pressure level decreases as the distance from the sound source to the sound receptor increases. Two accuracy tests need to be completed with differing source to receptor distances to measure the accuracy differences. The result will be a ratio expressed as a number between 0 and 1, 0 indicating no accuracy between the tests and 1 indicating no difference between the tests. The formula for calculating the difference in sound pressure level accuracy ratio takes the accuracy tests of a greater distance between the speaker and microphone and divides it by the accuracy test of a shorter distance between the speaker and microphone. The signal-to-noise ratio is an influencing factor in the accuracy of VADA speech processing software. The software's ability to reject ambient noise input has a direct effect on the accuracy of the software output. A minimum of 2 accuracy tests needs to be completed with differing signal-to-noise ratios to measure the accuracy difference with varying signal-to-noise ratios. The result will be a ratio expressed as a number between 0 and 1, 0 indicating no accuracy between the tests and 1 indicating no difference between the tests. Ambient sound or background noise will be defined as having a low sound pressure level rating between 60 and 80 decibels. This sound may be caused by mechanical devices, background conversations between people, or nature sounds such as wind noise. The formula for calculating the variance in accuracy with signal-to-noise ratio takes an accuracy test with a higher signal-to-noise ratio and background noise and divides it by an accuracy test with low signal-to-noise ratio and little background noise. Determination of accuracy for VADA speech processing software requires the tester to test and measure the 6 accuracy parameters outlined in this paper. The speech processing accuracy benchmark defines the testing procedures and measures parameters for speech processing software. The resulting speech accuracy benchmark score will be a number between 0 and 6, 0 indicating no accuracy and 6 indicating perfect accuracy. Test case 1 will have no background noise and a 30 centimeter distance between the sound receptor and sound emitter. Test 2 will have no background noise and a distance of 200 centimeters between the sound receptor and sound emitter. Test 3 will have background noise at 2 meters and a 30 centimeter distance between the sound receptor and sound emitter. A set of 15 test bank commands were created to test the word error rate, command error rate, authentication accuracy, and rejection rate of the VADA software. Test bank command number 3 contains ums and ahs, and test bank command number 4 has sharp noises including pounding, hammering, and doorbell ringing to assess the rejection rate of the VADA software. The testing hardware and software for this paper and presentation consists of a Samsung Note 5 with the software to be tested loaded on the device and given the correct device permissions to carry out the test. The software used is Amazon Alexa and Google Voice Search. A spreadsheet was developed using the formulas defined in this paper to calculate the accuracy rates from the raw data. The data from the test was input into the spreadsheet, and the results are shown for Google Voice Search and Amazon Alexa. The SPAB score for Google Voice Search was 5.673. The SPAB score for Amazon Alexa was 5.574, which gives an indicator that Google Voice Assistant speech processing service was more accurate than the Amazon Alexa digital assistant. Amazon Alexa was less affected by sound pressure level variance and less accurate executing the correct commands. The word error rate for both VADA systems across all three tests was nearly identical. Google Voice Service has an advantage in the command and authentication accuracy tests. A set of pre-recorded phrases should be developed using the process from the 2012 Language Recognition Evaluation paper. The phrases should not contain geographical or slang phrases. Creating the database of phrases and playing them through a speaker will eliminate any human variance when the commands are issued. The process of recording the scores would have been easier had the researchers used a video recording system. This would make it easier to review the test and ensure that the words, commands, authentications, and rejections were accurately recorded. The video camera should be positioned to record the screen output as well as record the audio of the testing session. The speech accuracy benchmark could be adapted to evaluate hardware. This could be accomplished by using the same testing techniques and changing hardware while using the same VADA system with each accuracy test. Research needs to be conducted into the effects of internet connection speeds on the accuracy of VADA systems. The speech accuracy benchmark score currently assumes the internet connection has no effect on the accuracy of the test. This assumption has not yet been sufficiently researched. Specifically, the question that is in need of research is, does the VADA system send a lower quality audio sample to the cloud speech processing service when the internet connection is slow? Speech processing software in VADA systems currently has no single set of accuracy measurement tests and scores that allows users, developers, and researchers to compare systems. There are several disparate accuracy tests and measurements. None of these tests take into account the full scope of output of speech processing systems. Combining the existing tests, word error rate, and adding the command error rate, authentication accuracy, and rejection rate gives the tester the ability to test the full scope of speech processing accuracy. Including the sound pressure level and signal-to-noise ratio variance into the benchmark score produces a score that takes into account the environmental factors in speech processing accuracy. The test data results revealed the difference in accuracy between the Google and Amazon systems. Comparing the word error rate, the command error rate, authentication accuracy, and rejection rate between the systems reveals which elements are most accurate in each of the speech processing systems. The speech accuracy benchmark score will give researchers, consumers, and developers an accurate testing method and score to compare VADA speech processing systems.